Greetings! In our previous videos, we managed to do all sorts of calculations for the simple cycle and the reheat gas turbine cycle, and we learned that the reheat cycle produces more work but is less efficient. And now what we do is to go for the promise that we said if this reheat cycle is associated with a regenerator, then the hot exhaust gases from point 7 may be used to heat the compressor exit air at point 2 and bring it to a warmer position at point 8. Point 8 and point 7 don't have equal temperatures, but still this means that to heat in the combustion chamber, we only need to add heat from point 8 to 3 instead of adding heat from point 2 to 3. And so we expect that this would make our cycle more efficient. Now, for the heat exchanger that should go in between, we usually define a parameter called effectiveness. And I define that parameter effectiveness here, which is, you see, the ideal point is that 2 is heat up to 7. So H7 minus H2 is our ideal. It doesn't happen, and you can only heat the compressor exit air to point, say, 8. So what we get is 8 H8 minus H2. And if you assume that an effectiveness of, assume effectiveness to be 0.8, and therefore H8 would equal H2 plus 0.8 times H7 minus H2, and the outcome for, we could just write all these values as CPT, cancel the CP zeros, and therefore T8 would equal 495 plus 0.8 times 971.4 minus 495, and T8 is 876.12 kelvins, which is considerably larger than 495. That was the compressor exit temperature. So this is an advantage, at least for the combustion chamber. So now QCC for the reheat, Q combustion chamber for the reheat equals CP0 times T3 minus T8, and that equals 1.005 times 1500 minus 876.12, and the outcome, Q combustion chamber for the reheat case, is 627 instead of 1010. Now it is 627, so it is 40% less heat to be added, kilojoules per kilograms. And that's a good number. What I do is just I use this space to calculate to calculate uh, our efficiency. How much has our efficiency changed? You see, eta for reheat plus regeneration equals 531, which was the work that we gained here in 6, 7 divided by now 2 heats added. One was um, from 8 to 3, and the other one was from 4 to 6. So it is 6 to 7 plus 2 to 3, and eta preheat plus R is 62.5%, which is considerably an improvement compared to 43.1, which was the reheat cycle, or 44.8, which was the original cycle. Now we have gained, in fact, from adding a regeneration and improved our efficiency to considerably higher values. Well, our final step in our very long journey with the gas turbine cycle is to know what happens for the real cycle and come closer to the real cycle. You see, for the ideal cycle, every process was ideal, but that is far from truth. Look, if we redraw the TS diagram, this is the TS diagram, and these are our two constant pressure lines of, say, 100 kilopascals and then 800 kilopascals. And I intentionally made the effort to make this distance wider because work to do in it. So the ideal compressor started from point 1 and ended up at point 2. Now the real compressor would start at point 1 and would end at point 2 sub r, which is the real compressor, and the compressor has some efficiency. Assume that eta for the compressor is 85%, which is a fairly realistic value. Something between 80 to 85% is common. Now, the maximum possible temperature for the cycle is 1500 kelvins. Now, for the ideal cycle, we would come to 800 kilopascals with no pressure loss. But in a real cycle, there is some pressure loss in the combustion chamber, perhaps delta P in combustion chamber is some 2%, say. And therefore, instead of uh, having the point 3 as it is, we would have another point, which is this one, which is 3R, and its pressure is less than the 800 kilopascal, which was the pressure for the ideal cycle. Now, we need a turbine which would run the compressor, and the ideal turbine would be 3R. It would no longer start from 3, but it would start from 3R, the real point 3, and would end up at point 4. Now, but the turbine has an efficiency, so it would end up at point 4R, which is the real point for the real turbine, the real exit point for the turbine. Now, the second turbine will start at point 4 and would expand to some point, which is point 5. It might be that the expansion happens to 100 kilopascal, but there's usually some um, um, exhaust at the exit, because after the turbine there must be some exhaust, and delta P exhaust could be, say, 5 kilopascals. Now, therefore, the ideal turbine would expand to point 5, but the real turbine would expand to point 5R, and the efficiency for the turbine, eta for the turbine, could be 90%, which is not an unrealistic value. Okay, so what we have is these are the real values that we could now use for our calculations. Well, we knew that the ideal compressor required a power of 223 kilojoules per kilogram. Now, the work for the compressor, but the real compressor is minus 223 and divided by 0.85, which is the efficiency of the compressor, and the outcome would be minus 262.3 kilojoules per kilograms. This is the efficiency. This is the real work, or is the work of a real compressor. That's the better language for saying it. This was the work required for an ideal compressor, and now we have calculated the work required for the real compressor. Now the question is, what would the temperature be at compressor exit now that you are calculating the real compressor? This WCR would equal Cp0 times T1 minus T2R. And therefore, we know that minus 262.3 equals 1.00, say 5 or say 45, not much different, times 273.15 minus T2R. And the outcome is T2R equals 534.1 kelvins. You see, T2 was 495, and now this is warmer. This was 495, and this is warmer, and it is 534.1 kelvins. This is the temperature at the exit. Now, here, point 3, we know all the properties, but for point 3R, what happens for point 3R? The temperature is still 1500 kelvins because you would add so much heat that the turbine blades could bear, but the pressure would be different. So at 3R, T 3R equals 1500 kelvins, but P3R would equal 800 times the pressure loss in the uh, combustion chamber must be deducted. So it is times 0.98, and that equals 784 kilopascals. So now that we know uh, point 3, we know the real point 3, then the high pressure turbine, which is in fact the compressor turbine, should be able to produce enough work to run the compressor. So the two works, real works, should be equal. The work required by the compressor was 262.3 kilojoules per kilogram, and the work produced by the real high pressure turbine is 1.005 times 1500, which is T3R minus T4R. And that would give us T4R, which is the exit pressure for the real turbine. So T4R would equal 1239 Kelvin. 1239 Kelvin. Now, point 4 is on the same pressure line, and it has an efficiency of 90%. So the point 4 is the ideal point for the high pressure turbine, and we shall use that efficiency of 90% just to return and calculate the temperature for point 4. So eta T, which is the turbine efficiency, equals the uh, the real work of high pressure turbine divided by W, ideal work of high pressure turbine. And just canceling CP0 from nominator and denominator, then you will be left with temperatures. So it would be 1500 minus 1239 divided by 1500 minus T4. And T4 is the exit temperature for the ideal turbine. And the outcome is T4 equals 1210 kelvins, which is of course less than 1239, which was the real turbine exit temperature. This is 1210, which is slightly lower. Now, this is the isentropic process, and by the knowledge of the temperatures and the pressure and the entry pressure, we would be able to calculate the exit pressure for the high pressure turbine. P4 equals P3 times T4 divided by T3 and to the power gamma over gamma minus 1. And just putting numbers to this, P4 equals 784 times 1210 divided by 1500 to the power 3.5 and the outcome is that P4 equals 369.6 kilopascals. So this is the pressure P4 or P4. R is the same pressure and equals 369.6 P4 kilopascals. That's the uh, in fact intermediate pressure between the two turbines. Now, so we know what this is. Look, this is an ideal point, and we just needed to calculate the intermediate pressure. But we now have all values for 4R, and we know that P4R equals 369.6 kilopascals, and T4R equals 1239 kelvins. Okay, now this gas would expand to 100 kilopascals, and of course, if we assume some pressure for the exhaust system, some pressure loss for the exhaust system, then we would need to allow for that um, pressure at turbine exit. We know that, but let's ignore that for the time being, and therefore T5 for this isentropic process equals T4R times P5 over P4 to the power gamma minus 1 over gamma, and that equals 1239 times 100 divided by 369.6 and to the power 0.286. And the outcome for T5, which is the ideal temperature of the second low pressure turbine, call it a power turbine, P5, T5 would be 852.51 kelvins. Well, the power turbine also, we assume that it has an efficiency of 90%, so that would bring us to calculate T5R, and eta T, which is the turbine temperature, equals 0.9, and that is the work of low pressure turbine, and that is the real work of the low pressure turbine divided by ideal work of low pressure turbine, and canceling CP0 like before, we would have 1239 minus T5R divided by 1239 minus 852.51. You see, the denominator is the ideal turbine work, and the denominator is the real turbine work. And calculating this would give us T5R, T5R to be 891.2 Kelvin. You see, compare this value, 85R, T5R, you see, compare this value with the value if it was an ideal expansion. Okay, you could compare it with that value, and also it's possible to write an efficiency for the overall turbine. It is possible to do that, and we usually do that in turbomachinery. We could write efficiencies for individual turbines or even individual stages, or you could write the efficiency for the whole turbine, and they would have different values. But that's a different subject. Now, we still need to calculate the work by the low pressure turbine and the work by the low pressure turbine, and the real work by the turbine is CP0, CP0 times T4R minus T5R, which are 1.005 times 1239 minus 891.2, and the outcome for the real work of the low pressure or the power turbine would be 349.5 kilojoules per kilograms. And the efficiency of this turbine, eta, equals the work, of course, the work of the power turbine divided by heat provided, which is the work is just what we calculated, 349.5. The heat added to the cycle is the CP0 times T3R minus T2R. CP0 is 1.005, and the temperature difference is T3R, which is 1500, of course, minus T2R, which is 534.1. And the efficiency for this cycle would be 36%. Compare this with 44.8% for the simple cycle, which is the ideal cycle, and we see that the real cycle produces even smaller efficiency than what we had calculated for the ideal cycle. Still very far from what we could possibly imagine with a Carnot cycle. But still, this 36% is not bad for a real gas turbine. In fact, this is the high end of what you could expect for Class E gas turbines. Usually, such turbines like V94-2 produce something around 33% to 36%, and they are Class E gas turbines. If they could rise this efficiency to 39%, then the turbine would be Class F turbine, which have been around for quite some time, and now Class H and other classes of gas turbines with higher efficiencies are also in production. Well, thank you very much for watching, and cheers.